Hello there, my name is Dag and I am a senior visual effects compositor based in Berlin, Germany. However, I'm also very interested in proceduralism and the like, so I dabble quite a bit in Houdini in my spare time. And today I would like to go over something called radial sorting with you, which in essence means to sort, say, points around some given center in a radial or circular way. And you might have already looked at that or looked that up on YouTube or some other media outlet and found one or two tutorials showing you how to do this. For example, the Indie Pixel YouTube channel has a nice tutorial on this subject, and I will post a link in the description for you so you can have a look at that tutorial as well. However, when I was looking to do such a thing as a radial sort that I needed for a project that I'm working on in my spare time, I found that in most cases the test case used for explaining how the sorting works and also how to implement it was usually a very ideal case, something like this that I have over here. Basically a perfect ring of points that have had their numbers or point numbers randomized. So if I actually switch on this randomizing sort node over here, you can see that now their points are randomized, and the task would then of course be to resort them properly again. You know, there's no geometry connecting the points, and for the radial sorting to work, you have to find a center position, which is very easy to do in this given case. But what if the case with the circle is not your actual user case, but rather you present it with something like this instead? Like this instead. I can switch off here. So what about this mess over here? How do you now do a radial sort? And specifically, how do you do this for every single intersection? So here's an intersection, and so on. How do you do this for every single intersection in this geometry? Well, that is what I plan to show you today. Okay, first of all, let's talk a bit about intersections and lay out a couple of ground rules for ourselves. The first thing is that we will be looking for and talking about points primarily, since what I will show you is a point sort method. And when I say intersections, I mean the points that are not simply somewhere on a single polyline, like somewhere around here, but are actually connected to multiple such lines. So here would be an example of this. Here will be an example of this as well. It's connected to 1, 2, and 3 lines in this case. We can define an intersection point in the following way. An intersection point is a point that has more than 2 connected neighboring points. So 3 or more. Because, of course, if it has exactly 2 neighbors, it will be somewhere on the line segment that is not its end and is also not an intersection. And if it has only 1 neighboring point, well, like over here, then it is exactly the end of a line or a curve. Okay, so let's have a look then. We can see that this here, for example, is an intersection. This has 3 arms, if you like, coming into it. Here's another one with 3. We've got one with 4, which is down here. And I think this one over here actually has 5. So there's a few intersections with varying numbers of arms or lines coming into them in this example. Okay, so what we need to do then is that in order to be able to sort around these intersection points, the first thing we'll have to do is, of course, we have to be able to identify those. And another thing that we'll have to do is to make sure that each primitive line segment that enters into an intersection has to have its own primitive number, and that each separate primitive can only end in one intersection, uniquely so. And if we look at the geometry now, I'll switch the primitive numbers back on, and as you can see, you probably can see it over here. You can see that basically this geometry has only 1 primitive number, and I can also middle click over here and see that we got 135 points, but only 1 primitive, only 1 polygon primitive in this case. So clearly, in order to do the sorting, we are going to have to do some prep work on the geometry first. The first prep thing to do then is to make sure that every section between 2 points is a primitive. So every section like this between 2 points has to become 1 segment. And you can see that now we only have 1 primitive number. And so basically what we can do then is we can hook up this to a convert line node. And now every segment between 2 points have become 1 primitive. So this is not ideal. We don't want everything to be split into primitives. We just want each segment between intersection points to be primitive. So we'll attach a polypath node to fix this, as you can see here. As you can see now, each segment between intersection points, like here, are actually a primitive and not between every single point or every single 2 points, pairs of points. So that's good, but we still have an issue though. If we look at this colored version, so we've got the prep stage here, which is prep stage 1, and we look at this color node here, and I'll switch off the primitive number. Now it's a little bit easier to see. We've already stated that each primitive can only end in one intersection. And the situation that we have right now is that most primitives end in two intersections. So for example, if we look at that yellow line here, we can see that it ends here and here. Now that's two intersections. Same thing for this one. And for most of these, they end in two intersections. And that won't do. So the solution to this would be to split each primitive into two at the midpoint. And there are various ways to do this. I've tried out a few methods, and we could solve this in Vex, but there is a very simple and effective trick that I picked up from a tutorial at the Dokai YouTube channel that I want to use today. And I will put a link in the description for that tutorial as well for you. So what we first need to do then, if we move down here, let's do it like this. Yeah. So what we first need to do is to double the number of primitives. And here's one way of doing this. So let's actually put the primitive numbers back on. We first branch off, then we reverse one branch, and we simply merge them back together again. So the direction of these polylines, if you like, have been reversed in one of the branches. And as you can see here, actually, if I just click here, middle click here, you can see that we went from having 96 primitives, 135 points, to now having the double of that. And, everything overlaps. But then after this, we add a carve node to our network and things suddenly disappear. We just see these little blue dots. And that is because right now, both the first and second U values in these parameters have been set to 0. And watch what happens if I take the second U parameter and I start to slide it up. You can here see, actually let's turn off the primitive numbers. You can here see that the primitives appear to grow out from the intersection point towards, the other section or the other primitive. Okay, first of all, that means that every primitive ending in an intersection has now the same directionality, which can be very useful for us. And secondly, if I set the second U parameters to exactly 0.5, the primitives will meet but do not overlap, except at the endpoints. And that we can fix by simply adding a fuse node. So let's see here. You can see that there are some numbers that overlap, some point numbers. We add a fuse node and voila, nothing is overlapping anymore. And if we now go down to this next one, so I've got a color node here, we can now see what has happened. So now it's pretty simple and easy to see that we have indeed split these primitives at the center and fused everything back together again. But then the question becomes, is this going to be enough prep for our case? And the answer is actually not quite enough. So let's zoom in on one of the really small sections. Let's just pick this section here. Hopefully you can see this. Yeah. As you can see, this here, for example, is an intersection point. And we want to radially sort these points that are, well, actually, let's put on the point number so you can clearly see. We want to radially sort the points that are around this intersection, that are connected to this intersection. However, if you can see that this point here, for example, is not just connected to this intersection, it is also connected to this intersection. And the same thing is true for this here, and for many other points in our network. And that would in fact mean that, let's say, if we're talking about this point here, we would actually be trying to radially sort this point twice, and that's not good. This is not what we want. So what does it mean? Well, it means that we have to make sure that our primitives have points that are also only connected to one intersection point. And in our current case, this is not always so. But luckily, the solution is pretty simple. We just have to resample each of these lines or our geometry with at least 2 segments. And this is what we're doing here in the resample node. And as you can see, we've set it to resample by polygon edge and 2 segments. And if we look at the same spot again, actually, let's go down to the fuse node because after the resample, we're fusing. So if we look at that same spot again, we have the intersection point here. And we can now see that we have points that are directly connected to this intersection point and only to this intersection point. So if we zoom even further in, we can see that these points that are now there because of the resampling that we did are now only connected to this intersection. And also, of course, another intersection over here. These points here are only connected to this intersection, and so on. And it is these points here, the closest one, that are only connected to a single intersection that we are going to radially sort. All right, so that is the prep done for our case. Let's maybe zoom out again. Let's do this and just look at this geometry like that. So that's the prep done for our case. Now, be aware that how much you would need to prep your incoming curve geometry here will of course depend on how you've set up those curves in the first place. For example, if all the incoming curves already have enough points per primitive segment, you might not have to do that resample that I just did. So this kind of stuff will vary from case to case. But for this example, we are done prepping, and we can now get on with the next step. So this is where we will turn to some vex wrangling. All right, what is it that we need first of all? For a start, for every single point, we're going to need to know how many neighbor points it has, and we also need to know exactly which points are the neighbors. So actually, let's switch on the points display here. Let us find a good candidate. Let's look here. Now, let's take this one here. Yeah, this one has 5 arms, so this is going to be a good candidate. And let's for now switch on the point numbers as well. We're not seeing anything in our spreadsheet, and that's probably because I need to show all the attributes. Okay, that's good. And we've got another thing to look at. Yeah, so I've got a sort node set to randomize, and I saw that I could put it to seed number 106, and that basically randomizes it so that the point that I'm looking at right here has the point number 0, this intersection point, which means it's going to show up at the top of my geometry spreadsheet, which is basically just makes it simple and easy to check when we're adding attributes, etc. to it. All right, so basically, let's do the wrangle node then. So we got ourselves a point wrangle. And the first thing I want to do is to define a couple of variables. So variables, and I'm going to have an int variable, so integer variable. I'm going to call it the center point. Then another one. No, actually not an int. I want a vector, of course, and I'm going to call that dir for this directional vector I talked about. That's the first thing. And then the next thing is I'm going to have to fetch that information that I just talked about. So we create a variable to hold an array of points, and let's not call it neighbor points or something. That will be an integer array. I will just call it npts for neighboring points, and the function that I'm going to use to get that will be the neighbors function, plural. And I can see it needs a geometry, and it needs to know about point numbers. So I'm going to just do 0 for the incoming geometry and point number, like that. So basically all my point numbers. And I'm also going to need to know the neighbor count for each point. That is going to be, let's just call that count. And again, there's a good function for that, neighbor count. Also really just needs 2 inputs here. Same thing, point number. And actually, let's output these things as a an attribute. So let's start with this one. The next one, which is not an array, let's call it count, and let's make that as count. Good. So let's look at what we've got now. All right. Let's just turn these off. I'm just wanting to know about the neighbor points and the neighboring point count. Whoops. So if you now look at the geometry spreadsheet over here, we can see that the point number here in this intersection is 0. And we can see which points are its neighbors. So these are the ones that we're going to sort later. And, correctly, this intersection has 5 arms going out from it. So we got 5 points. Okay, good. The next step then, what would that be? Well, that would be to calculate this directional vector pointing from our neighboring points towards their intersection point. So in this case, let's say this point here needs to have a vector pointing inwards like this, and the other ones as well. And of course, the same would be true for all the other intersections in the geometry. And we need this vector for the sorting to work. Okay, so for this, all of this to work, we first have to make sure that we start from the intersection points only. And then we will loop over the neighbor point arrays of these intersection points. So basically, we start from these points here, and we will loop over these arrays here. And once we're in the loop, we can calculate the vectors and then output these as an attribute onto the neighboring points. So let's do this. I'm just going to give myself a little bit of room. And all right. Calculate the the dir vector. I'm going to start with an if statement. And it's going to be if the count is larger than 2, because if this is true, I know that I'm actually on an intersection point. And once I'm inside the if statement, I'm going to write center point, which we created above, and I'm going to put my current point number into that variable, and then I can start my for each loop like that. Okay, so int, let's just say the current point number, and this is the array that we'll be looping over. Okay then, so here I will create this vector, and I want to call this center point position. I'm going to fetch that using a point function, and I'm going to use my incoming geometry, and I'm looking, of course, for my position, and I will be using this center point to basically fetch it from. Then next, I've got my dir vector to care about, and what I'm going to do here is I'm just going to copy this, and I'm going to take this position and then subtract with a point expression, or not expression, but a point function, again, the position, and this time the position of the current point number in the array. So basically, where I am in the loop, that point is getting subtracted from the center point position. And that should give me my directional vector that I want. And then my next task is then to create an attribute onto the points. But I cannot do something like this and say that this is equal to dir. This will not work in our case, because of course, that would put the vectors, or it would at least try to put the vector onto the center points, and not to the actual points around it, which is what we want. And so instead, I'm going to go for another function called the setPointAttribute function. And what do I need for this? Well, I need a handle, need a name, a point number, the value, and I need to put it to set mode. Okay, so I'm going to put the incoming geometry into there. I'm going to call it dir. I'm going to use the current number in the loop, and the value will be this dir vector that I just created. And then I just need to basically set it onto those points. So that should take care of that. But let me just, to be sure, let me just write an else statement as well, where for all the other cases, this dir vector is going to be 0. Just kind of as a failsafe. And then let's have a look at what we got. Did it work? No, it didn't. I have an error here somewhere. Oh yeah. Now it works. Okay, so something happened. And let's see, we can have a look here and see if we get a dir vector. Yeah, we've got something over here. But actually, to visualize this a little bit, let's add an add node. Let's delete the geometry, but keep those points. And now it's much easier to see that we did what we did. So if we zoom out, you can see that all of these intersection points, now there is a vector pointing towards it, or towards them, exactly the way that I want it. Good, that's working. Let's go back to our code for a second. I think the first thing that I'll do is to label this wrangle node. This one here. So let's just call it something like calculate dir vector. Okay. And then the next step will be to use this directional vector. Actually, we can switch it off, I think. It's the little red parts that you see here. The next step will be to use this directional vector to calculate a sort value. And for this, I'm going to drop down another point wrangle node. And I'll be labeling this up front. And I think I'll just say calc sort value. And let's have a look at that. Some space. First, I will grab that dir attribute that we just created, and I'm going to put it into a variable. So let's just get the dir, and that's going to be a vector variable called dir, and we're going to do it. Okay. And then we're going to create two float variables for the x and z values of the vector, because as you can see here, if you look over here, hopefully you can see this, I'm actually looking through the top viewport onto the geometry that is lying flat on the xz plane, hence the x and z values. So let's make a float dir underscore x, and that's going to be the dir x, and another float dir underscore z, and we're going to fetch the dir dot z from our vector. Now, I'm aware that it's not necessary to define these variables first or upfront like this, but for the purposes of the tutorial, writing it this way just makes everything visually very clear. Okay then, to calculate the sort value, we're going to use a mathematical function called atan2, so arctangent 2. I'm not going to try to explain to you exactly how this works mathematically in this tutorial, I'm just going to use the function. But I will give you a link or two in the description below in case you want to investigate that further for yourself. So let's do that then. Let's go here and let's do the sort value, calculate sort. And this time, I'm just going to output a float value, or a float attribute, call it sort, and I'm going to use that atan2 function. And as you can see, it takes two float values as arguments, and I'm just going to use my dir underscore x and my dir underscore z as inputs to that. Okay, so this is working. And as you can see over here in the spreadsheets, we are now getting some values on the points. So this is actually quite good. And that is actually the vex part done. So now we can finally do the sorting. For that, we're just going to put down a sort node really quickly. Push this up a little bit. We are going to sort points by attribute, and we're going to sort them by this sort attribute that we did. And voila! If you paid attention, you would have seen that our point numbers changed. But how exactly did they change? If we look closely, so for example over here, at any intersection, we should see that the neighboring points are now sorted properly around their intersection point. In our case, they will be sorted in a counterclockwise direction. And if we want things to be sorted the other way, so clockwise, we could just go back to our wrangle node and swap those dir x and dir z arguments in the atan2 function. But I'm actually perfectly happy with the result I have here. So for example, here you can see that we now have this number here in this particular intersection. This is the lowest number. And as we go around here in the counterclockwise direction, you can see that the value of the point number increases every step of the way. If I switch this off, so back to this state, no sorting, then here we have a low value, and then it increases, but then it decreases before it, well actually this is the lowest number, and it increases, but the last one is actually lower than this one here, so this is actually not a perfect sorting. And to verify that what I'm saying is actually true for all these intersections, we could have a closer look at a couple of those intersections, and not just this one. So okay, if we take the one next to it then, we have the lowest number here, then we go higher, higher, and higher, and that's good. If I switch it off, we have a low number, then a very high number. In fact, that is the highest number, and then we go down and down again. So this is definitely wrong in the sorting. If I turn it on, it is now right in terms of a radial sort in a counterclockwise fashion. We can have a look at another one. Let's have this one, for example. 34, 79, 380, and 438 is again correct. But turn it off. 125, 26, and then we go high, and then we go low. So this is actually not right. But when I turn it on, we do have correct sorting. So that's actually exactly like I expected. One little thing for the intersections that have exactly three arms, or basically three intersecting, or not intersecting, but three neighboring points, whether or not you do this sorting or not isn't really going to matter, because they will have some kind of radial sort, either clockwise or counterclockwise anyways, due to the fact that there's only three possibilities. So really the sorting, whether or not it actually is correct, is really only truly visible if you look at intersections with 4 or more arms. So we can have a look at this one as well. If we turn it off, what do we have? So this is 19, then 295, that goes up, further up, and then down, so that's wrong. If I switch it on, we have 41, 65, 403, and 434. So this is now correct. And as you can see from this, all the neighboring points to each intersection has now been sorted radially. But if we want to have a real look at how solid and stable this actually is, we can go up to that other sort node that we have up here. This one actually randomizes the point number with the seed value. So if we zoom out a little bit now, hopefully you can see this well. When I start playing around with this seed value, you can see that all the points, so if we look at places like here, 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 you can see that all of these points are changing randomly depending on what seed I'm out inputting. But exactly the points that we identified as the neighboring points to an intersection, they are locked. Can you see this? If you look at the original one that we had a look at, you can see that these points are locked and all the other points around them are not. Same thing is true for here. The other points are changing randomly, but not the points that we actually wanted to sort. Put that back to this. And actually, what's happening is that the sorted points are now locked to some given point number that will ultimately have been defined by that sort value that we calculated. And as you can see from this, is that nothing that we do further up the chain, as far as the point numbers are concerned, influences the point numbers in our radial sort anymore, which is great. This actually works really well. And it will work on any incoming polyline geometry as long as this actually has intersection points, and as long as you've properly prepped the geo before you get to your vex code and sort node. So that's that. Okay, so now you might be thinking, well, that's all neat and everything, but why the hell would I want to go through all of these steps in order just to sort a few points this way? What on earth kind of use can I have of this trick? And I understand what you mean if this is what you think. At first, it looks a little bit underwhelming, to be honest, but here's the thing. If you have these points here, around each intersection, if you have these points radially sorted, so either in the counterclockwise direction or in the clockwise direction, the point numbers are going consistently from low to high numbers around the intersection point. And you now, after the sort, run the code to find the intersection points and their neighbors again, and you then run a sort function on the resulting array, you actually have an interesting situation. Because when you have such an ordered and consistent array, and the same thing is true for the points in your geo, you will be able to do things like find out, for example, for each neighbor point, so for each of these points, which is its next point around the intersection, and of course also therefore its previous point around the intersection. And that is when things become a lot more useful. So not really flashy, but still cool. If you then add the position of the intersection point here to the mix, because remember that we had to calculate that point position in order to create the vector that we call the direction vector or the dir vector. So for example, if I go back up here and I have a look, this dir vector here, we use the setPoint attribute function to export that onto these points. But we could also take this position that we calculated and we could have exported that as well. And if we had done that, or if we did this, in other words, exporting it as an attribute onto our radially sorted neighbor points, we could do things like calculate the angles between these neighbor points and by implication the primitives extending out from all these intersections. And that is a very useful information to have. Now, I'm sure you can think of many use cases for what to do with that information in a setup. Okay, now this is a tutorial about the sorting itself, so there's no space for specific use cases that I can demonstrate, but I did put together an example to show you really quickly what I mean. So over here, I have a little example. I can zoom in on this a little bit more. And I basically just put these curves together. So I put these curves together and I ran them through a very, very similar prep stage and did the sorting as well. And then I did some extra code here. And so we're at this point here where we have been outputting a few extra attributes onto our points. And if I now look at the next point attribute here and I turn this on, we have our point, or basically our points display on. And if I look at point 0 here, it tells me that the next point around this intersection in the counterclockwise direction should be point number 1, which it is. The next point from point 1 should be point number 2, which is here. And this one tells me that it's point 9, that is the next one for it. And that again is true, and so on. And I can demonstrate that if we put on the previous, so if I turn this one off and we just look at the previous point, well, now the 0 or point number 0 here tells me that it's point 10, that is its previous point. And again, point 10 tells me its previous point is point number 9, and so on. And that's really interesting. But as I said before, it gets even more interesting if we actually look at those angles. And I can show you that as well in my example. So if I turn on this one, it's called angle next or ang next. Now you can see that I've been able to calculate the angles between, well, in this case, this angle here will be, or this angle here, as you see, will be the angle between this point and this point. So basically it's next angle, or the angle between this point and its next point around the intersection. And if I go up here again, and I start moving these things around, you can see that the numbers update, but of course only the relevant numbers update, because now I'm looking at the next angle. So basically, If I'm moving this, the angle here should update, but also this angle behind it should update. And the others should not update because they're not really moving anywhere. And vice versa, if I look at the previous one, it still also works. Yep. So if I move this one again, now it's going to be this angle here and this angle here that gets updated. And interestingly, I can also do things like move them around, like this arm here, and it keeps, it doesn't break just because I'm overlapping here, which is really nice. And we can double check that by, let's turn maybe both of these on. Yeah. So here we have a next angle, and let's make that roughly 90 degrees, like this. This looks kind of correct. If I now take my other arm here and I put it roughly in the center, we should get it to be about, 45 degrees or so. So for this one here, the angle here is 45 degrees, and its previous angle is 44.6 degrees. So it's roughly in the middle. So this works really well. It's also very solid, very stable. And all of this is only possible because of that radial sort that we did a minute ago. So hopefully now you can see that due to this, we're able to extract further information that can be very useful for a number of things in Houdini. And with that, the tutorial is at its end, and I will say goodbye for now. Thank you very much for watching, and have a nice day.